All right, I got that out of my system. Let us begin. Begin with a word of prayer. Dear Father, we thank you for this day. Thank you for these students. Just ask you to bless this class today, Lord. In your name I pray. Amen. All right, so yeah, let us try to. So basically, what I did last time was tried to explain what the exterior measure was, according to again real analysis by Stein and Shakarachi. I'm sure I'm saying that wrong. But this is, of course, Volume 3 in the Princeton Lectures in Analysis series. And it's a joy. Really, really nice book. I really like the way he does it. But we defined the exterior measure which was m star, right? M star. And how was that defined? What did we say? What was the definition of this thing? So m star of E was the inf of the sum j equals 1 to infinity of qj like a so for any subset of Rd, where this is taken over, as he says, all countable coverings of E. So E is a subset of the union j equals 1 to infinity of qj. What were the qj's? Cubes, yeah. So you're taking a bunch of cubes, you're covering the set that you're interested in with cubes, right? And you look at all possible countable coverings of your subset by these cubes, take the inf of that, and that's the exterior measure. So we spent a long time talking about the properties of this thing, right? And oh, you were, King, for some reason I'm thinking you weren't here last time. I'm an idiot. You were here last time. Duh. I'm thinking of the class before that class, right? Duh. Moron. All right, so let me get on with it. And then we used that, we observed various properties of this exterior measure, right? I made a series of observations, and it was monotonicity, the countable subadditivity, the fact that we could replace the exterior measure with the inf of the exterior measure of O, where O is taken over all open sets covering E. So you could basically replace this with O open and take the inf over such things, all right? And let's see here, what else do we have? If the set we're looking at was the union of two sets and the distance between those two sets was non-zero, right? Then the exterior measure is equal to the sum of the measures of the subsets, the disjoint subsets. And finally, if E is observation 5 was if E is a set which is the countable union of almost disjoint cubes, right? Then, right, well, I'll recount that. This was kind of a nice, so the exterior measure of the union j equals 1 to infinity of qj, all right, is equal to the sum, j equals 1 to infinity, of the exterior measure of, well, the exterior measure of qj, that's true, but what is the exterior measure of qj? It's just the volume of the the jth cube there. But this assumes something, right? Assuming what? The cubes are almost disjoint. What's that mean? The edges, right, they intersect at most along their edges, right? So the intersection of their interiors is empty. All right. Then, at the very end of class, we said, okay, well, that's going to define what we mean by Lebesgue measurable. So definition. E, a subset of RD, is Lebesgue measurable or simply measurable if for any epsilon greater than 0, there exists open set with E contained in the open set, and the exterior measure of the open set complemented by E is less than or equal to epsilon. And then he says, if E is measurable, then we define its Lebesgue measure by just, in such case, right? ME is by definition the exterior measure of E. All right. And then I think I listed a number of properties, right? Did I write down the properties last time? I think I did. Let me state them again. Property 1, open sets in RD are measurable. Property 2, if the exterior measure of E is equal to 0, then E is measurable. In particular, if F is a subset of a set of exterior measure 0, then F is measurable. A countable union of measurable sets is measurable. Closed sets are measurable. The complement of a measurable set is measurable. Finally, the countable intersection of measurable sets is measurable. All right. And finally, theorem 3.2, if you have a sequence of disjoint measurable sets and E is equal to the union of all of them, then the measure is the sum of the measures. So theorem 3.2 is kind of the ultimate statement here. So you have E1, E2, ... disjoint, measurable sets. Then E equal to the union, j equals 1 to infinity of Ej is measurable. And the measure of E is the sum, j equals 1 to infinity of, the measure of Ej. Now, if I had 10 hours of class time, I could prove all these things, right? I mean, it would take me a while to actually flesh them out. Okay, so that's the backdrop, that's the setup. Basically, this Lebesgue measure is something, it's a little bit sneakier, right? A little bit sneakier than the exterior measure. It almost feels like it's the same thing, but it's not, is it? Not quite. Yeah. All right, so furthermore, now we're finally getting something new. If we have a countable collection of subsets of RD that increases, so consider E1, E2, all subsets of RD, such that EK is a subset of EK plus 1, all right, for all K. And if we form E as the union over all of them, right, then we write, and this notation is, I think, really neat. EK goes to E. So that's a definition. And a notation. What if, on the other hand, you had, what do you think this would mean if I had EK goes to E like that? What would that mean? What would that notation mean? Yeah, what would decreasing here? That would mean like EK contains, yeah, EK plus 1. So I could say something like this: E equals the intersection, J equals 1 to infinity, right, of EJ. That, of course, is a subset, subset of E3, subset of E. Right? So if you take the intersection over all of them, and if that intersection is E, then that's what this notation means. We've got a sequence of subsets of RD that the intersection over all of them is E. That makes sense. I mean, the sequence of sets is converging to E in that sense. All right. So he says the sequence of the subsets decrease to E in this sense. All right. All right, great. This is a new kind of marker. I was testing it out. The secretary asked that we test the markers out, so I'm testing it right now. Let's see if we like these ones more. Take your guys' opinion. Let's see here. This is a fresh one, to be fair. So corollary. Corollary. Come on. 3.3. Suppose E1, E2, are measurable subsets of RD. Point number one, if the subsets EK increase to E, then the measure of E is equal to the limit. Oh, this is neat. Look at this. Limit as big N goes to infinity of En. Yeah, they're supposed to be, yeah, thank you. Otherwise, it doesn't make a bit of sense, does it? Thank you. And 2, if ek decreases to e, and the measure of ek is less than infinity for some k, just for some k, then, I mean, that's all it takes is for the measure to be less than infinity for some k, all right? Then the measure of e is equal to the limit as n goes to infinity of the measure of en. So this is a very important corollary because what it means is that the concept of measure plays nice with countable unions and countable intersections. That, you know, if we have some sort of sequence of subsets, then we can capture the measure of the limit set in terms of the measure of the sets being limited. That's very nice. Do you understand this? Does this make intuitive sense to you? Like that there's some k, right? Because if there's some k, that means that the intersection fits inside those, right? And if the intersection of all the sets fits inside that, if the measure of that is finite, then of course, if you further intersect it, it just stays finite. There's no way you can like somehow have something that's finite and then keep intersecting and somehow have it become infinite, you know, because of monotonicity. All right. Theorem 3.4. I guess I could prove this, but I think I'm going to resist the temptation. Theorem 3.4. Suppose E is a measurable subset. Measurable. Then for every epsilon greater than 0, point number 1, there exists open set O with E contained in O, and the measure of O complemented by E is less than or equal to epsilon. Oh, by the way, does this look, I mean, so you guys, students, which marker do you prefer? Can you even tell? You can't even tell. This one is so much nicer to write with. Like the difference between this and that, I can't even explain. And it's weird because
they give us those ones at the library.
and I don't know why. I mean, it shouldn't be so different. I mean, they're almost the same size. You know what it is? This one is tapered down. It's like not as much to hold on to when you're writing on it. And there's something wrong about the shape of the tip. I don't know what. But yeah, I find this one is much less like stressful to my hand. I don't know what it is. Yeah, sorry. I am not a sponsor, but sorry, I'm an idiot. I should monetize my channel, right? There exists a closed set F with F a subset of E, and the measure of E minus F is less than or equal to epsilon. All right. Okay. What's the point of this theorem? He says, what follows provides an important geometric and analytic insight into the nature of measurable sets in terms of their relation to open and closed sets. Its thrust is that, in effect, the arbitrary measurable set can be well approximated by the open sets that contain it, or alternatively by the closed sets that it contains. Okay. Well, let's see here. What do 3 and 4 say? If the measure of E is finite, there exists compact K with K inside E, and the measure of E minus K is less than epsilon. And then 4 is weird. If the measure of E is finite, then there exists a finite union F union J equals 1 to n of Qj closed cubes such that the measure of E triangle F is less than or equal to epsilon. What does that mean? Well, he tells us that this is the so-called symmetric difference. That is specifically E minus F unioned with, well, F minus E. What's that look like in terms of, maybe I should try to draw a picture of 4. Shall I try? What's going on here? How should I picture this? The measure of E is less than infinity, so generically speaking, E. Okay, fine. And what else? There exists a finite union of closed cubes. So, this again, huh? Whatever. I should probably have picked a different color for my E, right? Oh. Then what's happening? Redefining it so that my cubes cover it. Sorry, guys. Oop, can't do that. Fine. All right. Something like that is my closed cubes which cover it, such that what is the symmetric difference of E and, so the F is the blue boxes. Yeah, let me try to color code, foolishly try to color code one of those. Let me at least, I'll start with this one, probably I picked wrong, but E with, oh, F doesn't have to cover E. Okay, so let's make this more exciting. We'll put a hole in it, right? Oh, it doesn't look like it's a hole, though, does it?
No, it just looks like you
Hole. Okay. Sorry. So E minus F is what? It's that hole. Is there anything else? Everything else is in. Wait, no, I think you're. Wait a minute. E. What is E? The black. Oh, okay, so everything else is removed. Everything else is covered by F, because F is the blue boxes. Okay. All right. I'm on board. I'm good. You are looking at this, right? Okay, because I would be full of infinite sadness if at the end of this discussion I found out it was over there. It's good. It's good. Perhaps not infinite sadness, but finite but large. So F minus E, what's that? Everything outside. Everything outside of the black, but in the blue. So like this, the overshoot, right? So I think if you draw this picture and think about what that means, that's pretty neat, what 4 says. You can get a sense of what it's actually saying. It's
saying you give me an epsilon and I can construct an arbitrary group of boxes with cubes such that the difference between my construction and the original, whatever the original space is arbitrarily small. The smaller your epsilon.
Symmetric. Oh, and I'm supposed to take the union of those two things. Did I do that right? F. I think that's. Oh, but I'm making that small. Oh, okay. So you're. Oh, okay. See, I see what you're saying. You're saying that means that we can make the covering by cubes as close as we want in this technical sense to the given measurable set. Yeah. Okay. Sorry. He then, on page 22, talks about the invariance properties of the Lebesgue measure. All right, so the crucial property of Lebesgue measure in RD is its translation invariant. And here's why. If we take a measurable set, E, then we can define EH. What's E sub H going to be? I would usually denote it H plus E, right? Which as a set is H plus X, such that X is an E, right? It's literally the translate of E by H. We can prove that the measure of E is equal to the measure of EH for all H. So. And he says, with the observation that this holds for the special case when E is a cube, one then passes to the exterior measure of arbitrary sets and then sees from the definition given that M star EH is equal to M star E. So, does that make sense? What's that? He says that, first of all, it's clear that if we take, Q as a cube, right, and we look at QH for a cube, then the exterior measure of this is equal to the exterior measure of Q. So you can show that. I mean, essentially, I don't know. It depends on how finely you want to cut things here, but I mean, the volume of a cube is the same as the volume of the cube after it's been translated. So that's why this is true. But of course, he's defined that in terms of countable, I mean, in terms of coverings of cubes by open sets and all kinds of technical blah, blah, blah. So like, there's probably actually something to prove there, the way he has things set up. But anyway, that's true. And once you know that's true, then if you take a measurable set E, what can we do? Any measurable set E can be what? Yeah. Oh, right. It's the where yeah. Thank you. I've lost my way. It's the what? Oh, right. M star is the inf. M star of EH is the inf of what? Am I doing? Is that? I'm not. I'm sorry. I've brain is skipping. What's that stupid thing? QJ taking around countable. Oh, the volume. So this is over the, volume of, let's say, Q, and let me call this Q tilde J, where, the union over Q tilde J includes EH, right? But I think you can, so of course this is equal to E plus H, right? And so I think you can prove that the union J equals 1 to infinity of, Q tilde J parentheses minus H perhaps is covering E. So like if you have these cubes covering the translate of E, then you can shift them back and get a corresponding covering of the untranslated E. But that see, if you're going to robocall me, you got to start talking faster. All right. Anyway, so the point is that golly. But of course, we could trade this for the inf of, something like, this is a sketch of the proof. There's probably an improvement to this, but this is my knee-jerk. So like I can
I wonder if that's the video game club. They meet up here.
the video game
Yeah, I
club.
walk past it like every Friday.
It's relatively mellow here. Like, compared to like the distractions of abstract algebra 2, this place is chill. abstract algebra 2 is just like there's people talking in the hall. It's just nonstop distraction. But anyway, I know this is equal to this because this is just a translation of the q tilde j cube. But then what I'm arguing is that, well, I'm arguing that not only is this a covering of the original E, I'm arguing that any covering of the original E can be put in this form. Like you can always look at any covering of the original E as being the translate back of a covering of the shifted E, which means that this inf is just the inf over all cubical coverings of the of E, which means that by definition this is the exterior measure of E. So something like that's the argument. Because it's true for a cube, it's true for the exterior measure. And then because it's true for the exterior measure, it implies that it's true for the Lebesgue measure, as the Lebesgue measure was defined in terms of the exterior measure. So this is the translation invariance, which of course is important, because that's one of the fundamental observations, is that, you know, integrals have a translation invariance. Ooh, wrong book. Okay. And he also proves a relative dilation invariance of the Lebesgue measure. He mentions that if you take, he asserts that if we look at the measure of delta times E, you can prove that it's equal to delta to the power D times the measure of E, where delta E is just equal to delta X, such that X is an element of E. And here we're assuming delta is, I suppose, greater than or equal to 0, right? Yeah. All right, that brings us to our discussion of sigma algebras and Borel sets. All right. So what is a sigma algebra? Here's definition. A sigma algebra is a collection of subsets of Rd that is closed under countable unions, intersections, and complements. Now, I'm relatively certain of this. I should say that this is the definition of Borel sets in this book at this juncture of time. It seems to me that this is a more general notion that could easily be defined for a topological space, right? You could talk about a sigma algebra in a more general context, in a topological context. Remember, this book at this juncture in time is not something that's already covered abstract point set topology, right? So it would be grossly inappropriate for this book to talk about abstract topology at this point. So they're giving us the definition of sigma algebra that is appropriate to the context of this book, not the more general one. Yeah? But anyway, here it is. It's a collection of subsets that's closed under countable unions, intersections, and complements. So what's an example? What's that? The empty. Some examples. Some more or less vacuous. The empty set. Does that actually work? I mean, empty collection. I should say not the empty set, but the empty collection. Yeah, okay. I don't know. I can, yeah. Mhm. Oh, closed under complements. There's nothing to complement in it, though. He's not saying the empty set. A collection containing the empty set would not be an empty collection. Right, we could take the power set of RD, the set of all subsets of RD, including the empty set RD and everything else under the sun. In other words, the discrete topology, right? Oh, the indiscrete topology, as it's sometimes called. So you're saying RD and the empty set will also work? Countable unions, countable intersections, they're okay. Complements, yeah, you got them. Yeah, I guess you guys are right. That also works. Yeah, okay, cool. Okay, but what is the Borel? The Borel sigma algebra what's that? He says it's the smallest sigma algebra that contains all open sets. All right, so what is it not? So, and you know, again, what does open mean here? Remember, metric open. So, this is not going to do it. Wouldn't be prudent, right? Now, that's a candidate. It's got all open sets. But yeah, it's got way too much. It's not the smallest sigma algebra, right? Not the smallest one. So what he says is that he says any intersection not necessarily countable of sigma algebras is again a sigma algebra. We may define the Borel sigma algebra of RD as the intersection of all sigma algebras that contain the open sets. So basically he says, okay, so I think his notation BRD is just the intersection over all such sigma algebras. I mean, the collection over, and what I mean by all, I meant to write such, not such that, all such. And by such, I mean the ones that contain open sets. Now, why is that intersection non-trivial? Yeah, it has to contain the open sets. And also, it's non-vacuous, right? There is at least one such thing there, right? So it's a thing. He says this shows existence and uniqueness of the Borel sigma algebra. Aha! He says, furthermore, since open sets are measurable, we conclude that the Borel sigma algebra is contained in the sigma algebra of measurable sets. Right? So in terms of like, I guess that's the question is, the obvious question you want to ask is what's the relation between this Borel sigma algebra and the Lebesgue measurable sets, right? So what he says is, all right, let me see here. Since open sets are measurable, we conclude that the Borel sigma algebra is contained in the sigma algebra of measurable sets. So he says, okay, first of all, something I have not said yet, but I should have said, another thing up here is, collection measurable subsets of RD, right? Is that, if we look at Lebesgue measurable subsets of RD, is that an example of a sigma algebra? Right? I mean, we just have argued that the, measure of countable unions, countable intersections, and complements all play nice with the measure. They give us measurable sets. The thing I just erased here, right, among other things, parts of that. Okay, anyway, so that's a sigma algebra. And it contains the open sets, right? Open sets were measurable. All right. So then he asked the question, do there exist Lebesgue measurable sets which are not Borel sets? All right. The answer is yes. He says, from the point of view of Borel sets, the Lebesgue sets arise as the completion of the sigma algebra of Borel sets. So I guess I don't know if I've said that. I'm not sure this is true. So I think he's saying that this is not, how to say this? Stupid. I'm sorry, guys. I'm missing words here. Yeah, this is not equal to the, which is a subset of which is my question. Okay, so the point is that this is a subset of the measurable subsets. Lebesgue measurable, of course. What's that? Yeah, he is saying it is proper. There exist Borel sets, I guess you could say, which are not measurable. Wait a minute, no. Other way around. There exist measurable sets which are not in the Borel sigma algebra. All right. He says, from the point of view of Borel sets, the Lebesgue sets arise as the completion of the sigma algebra of the Borel sets. And to get from, so basically to get from here to here, you're adjoining sets of measure 0, as he says. That's basically what goes on here. So the sets of measure 0 are the ones that are not necessarily in the Borel sigma algebra. And that kind of makes sense, right? Because sets of measure 0 don't seem very open. So by necessity, why would they be in the Borel sigma algebra? The Borel set, the rational number is a Borel set? Right. Yeah, so I'm not necessarily. Some of the sets of measure 0 are in the Borel sigma algebra, right? Just not all of them. There exists a set of measure 0, which is not in B sub RD, but is measurable. Well, it has measure 0, right? So, and corollary 3.5 makes this more precise. He says, a subset E of RD is measurable if and only if E differs from G delta by a set of measure 0, or if and only if E differs from F sigma by a set of measure 0. You might wonder what G delta and F sigma are. What is G delta? G delta is countable intersection. If a set is G delta if it's formed from the countable intersection of open sets. A complement of such things is the so-called F sigma set. Anyway, this is whatever. Okay, great. Now, the only reason I'm talking about this at all is many books and many people who think about these things more deeply than I do, they might start with just an abstract discussion of sigma algebras, work on that for a while before they even open the door to discussing what a measure is. to them, this discussion of this sort of almost abstract algebraic sigma algebra structure is the starting point for measure theory, which then leads you to the discovery of the measurable sets in this sense. I think Dr. Skambordis is such a person, because when he was talking about measure theory to a student a few years ago, he said a lot of things about sigma algebras before he said much about integrals. Right? Okay. And then he gives this example of a non-measurable set. I would encourage you to read it. It is dastardly. Finally, measurable functions. There is hope yet. We'll finish this what I'm supposed to today. So, of course, all of this is just trying to build up the definition of the Lebesgue integral in the next chapter, okay? And the reason we want to do all of that is just to sort of repair, in some sense, the holes in the Riemann integral, and also just some sort of annoying I don't know what the word is. Some of the quote-unquote counter examples of classical analysis are repaired by this concept of almost everywhere. So here we go. Let's keep at it, see where we get to. Measurable functions. So definition, characteristic function of a set. What's that? This is chi e of x, which is 1 if x is in E, and 0 if not. Right? If left to my devices, I would probably denote this like this. It's the Kronecker delta. Yeah. Okay, fine. The index is continuous. Why be bothered? What's that? Just write what? Change the chi. No, I'll leave it. It's fine. This is standard. All right. And he says the Riemann integral is in effect the class. Okay, so what are the functions which are allowed in the theory of the classical theory of Riemann integration? He says those are the step functions. What are step functions? So these are not actually the ones that are of interest to the Lebesgue theory, but I guess they're probably allowed, but they're not. We can do better, is what I'm trying to say. Step functions have the following form. It's important to contrast step functions with simple functions that are following. K equals 1 to n of a sub k chi rk. Here, ak constants, right? And rk are rectangles. That's a step function. A simple function is what we need for the Lebesgue integral. It's a more general notion. A simple function what's a simple function? F equals to sum k equals 1 to n of a sub k, characteristic function of ek. Right? Where ek is what? Measurable, right? A measurable set of finite measure. the Lebesgue integral that we'll define in the next chapter will allow us to treat things like simple functions. You can already appreciate why that's such a vast improvement, because you know something about how much more imaginative a measurable set is than a rectangle, right? Measurable set can just be a collection of points, Okay. So now you guys are going to have to help me with this. This notation I am not good on yet. I don't understand this fine. This makes sense to me. Apparently, I wrote it down last time, right? So this is what we mean. We're allowing functions to be possibly infinite, in a sense, all right? F of x belongs to the extended real numbers, as he said. F is finite. What's that mean? This is finite valued. F is finite valued if minus infinity less than f of x less than infinity, right? Finite valued. He says, in the theory that follows, in many applications of it, we shall almost always find ourselves in a situation where a function takes on infinite values on, at most, a set of measure 0. Definition. Measurable function. Woohoo! This is a big one. A function defined in a measurable subset of E is measurable if for all A in R, the set F inverse of, look at this, closed interval at minus infinity to A not included, is measurable. He says, to simplify our notation, we shall often denote the set simply by, all right, well here, let me put the notation up here. So this is, what that means, of course, is x in E such that f of x is less than A. So this, I said it in words, a function defined on E, right? So I'm assuming E is the domain of the function, okay? So a function defined on a measurable set is function defined, we use measurable, probably an F. I jumped there's kind of an important phrase here, is said to be measurable. If this. I still have said it wrong. Good grief. A function defined on measurable E is said to be measurable if for all A, the inverse image of this is measurable. We are defining measurability of the function, all right? Okay. Now, he has a notation, a sneaky notation for this, all right? And his notation is that this is, what is this? I think he calls this F less than A. Does that make sense?